So what I'm about to write down, you don't need to write down, okay? So for just a moment, I just want your eyes and your ears while I take the old information and sort of guide you into how we're going to be talking about it today. In the last unit, we solved systems of equations. That means two or more equations with two or more variables. Okay, stuff like that. We solved it, okay? That is a system of equations. If I were to rewrite that in matrix form, it would look like this. What are some things you notice between these two ways of writing? What's something? Just anything. There's no variables in the second one. That's a matrix. There's no variables. Okay, what else? The line means equals, that vertical line, right? What else? There is a guy. Thank you, sir. Thank you, guy behind me. What else? What? The brackets. How did they change? Yes. They went from squiggly brackets to straight brackets, right? Or squiggly wigglies, curly brace, whatever you want to call that thing. Now they're just straight brackets, okay? And they're on both sides. What do you think is going on? Why is this 9, 12 over here and these numbers are over there? These are x and y's, right? This is from the left side of the equation. The 9 and 12 is from the right. Does anybody remember what we call numbers without variables on them? Constants, okay? And what do we call these numbers that came out from in front of the variable? Coefficients, okay? So all this stuff we're going to be talking about. So while you have a packet of stapled papers there, it makes you kind of feel like we're going to be doing a whole bunch of stuff. We're kind of not, because we're cutting off several of the problems, and a lot of the stuff in the packet is just sort of vocabulary or conceptual things, all right? None of them are going to be hard at any given time, but by the end of the lesson, you might feel like I just threw a whole bunch of stuff at you, which I will. And it might be kind of hard to keep it straight, but you'll get used to it really, really fast. All right, so we're beginning with, so now we're going to start taking notes, okay? We're beginning with just the definition of a matrix. Besides a movie with Keanu Reeves, there, I got it out of my system. Sounds bad. A rectangular arrangement of numbers in rows and columns enclosed by brackets, which might have meant nothing to you if we hadn't done this. Do you see how that's a rectangular arrangement of numbers, right? In rows and columns. Rows go this way, left to right. Columns go up and down, enclosed by brackets. Okay, so that's what a matrix looks like. We name matrices with capital letters. So if I wanted to give that one a name, give me a letter. E. Okay, that would be matrix E. Okay, capital. And we talk a whole lot about the size of a matrix. And we have to, and that's basically just its dimensions. It's rows and its columns, but it has to be done in a certain order so that everybody in the world is speaking the same language, right? And also, when we get to matrix multiplication, that order is important as well. So if I was looking at a matrix and I wanted to know the size, or dimensions is another way of thinking about it, or order of a matrix, we always list the number of rows first and the number of columns second. And by the way, matrices help us solve systems more easily, is why we have them. Do you remember which way rows go? Left or right, up or down? Left or right. Columns, so I don't know I don't know when I learned this. I've been doing this, I think, since high school. This, for some reason, helps me remember which is which. Rows left and right, columns up and down. But probably a more sort of common sense way to remember is columns on a building, which way do they go? Up or down, right? So it's always, columns are vertical, rows are horizontal. And we talk about rows first and columns second. When we're talking about the size or order of a matrix. Does anybody need this up anymore? You got what you need? Okay, so we have this matrix here. What's the name of this matrix? A, all right. Matrix A is, we want to do the size. It's rows first. How many rows are there? 2, right? Rows go left to right, so there are 2 of those. And how many columns? 3. column 1, column 2, column 3. Okay, or 2 by 3. Okay. So please understand when I'm asking you for the size or the order, I'm not asking you for any particular information about what's inside. I only want to know how many left to right things are there and how many up and down things there are. But if I did want to start talking about what's inside, like if I wanted to specifically talk about any one of these things, I would say, well, first of all, how many numbers do you see in there? 6. Okay, so there's 6 things inside. We're going to call those entries. Okay, those are entries in the matrix, which did not have to take a red or blue pill. Okay, I'm done. I'm just done. That's my last one. The entries are represented by this notation. So here's what's going on in this notation right here. First of all, is this an uppercase or a lowercase a? Okay, so when we name matrices, we use uppercase letters. Okay, that A stands for everything in that matrix. But if I want to pick out one piece of that A matrix, I'm going to use a lowercase a to talk about that specific entry. And then I've got this subscript here, this I and this J, where I is the row for the entry, and J is the column. So the lowercase a just means I'm talking about a specific number inside the entire matrix, capital A. But to identify where it is, we list the row number and the column number. So in this example right here is asking me to find not A sub 23, it's not a 23. It's A sub 23, where 2 stands for row 2, and 3 stands for column 3. And the entry is going to be where those things overlap or intersect. So I'm going to look at row 2. This is everything in row 2. Here's row 3. What is the entry at their point of intersection? -5. So A sub 23 is -5. That's the answer to this bottom example right here. Okay. So again, it's not A sub 23. It's A sub 23. Where does row 2 and column 3 intersect? And that's entry at that point is -5. Does anybody need any of this up anymore? So you take a moment for these two matrices, write 2 things. It's asking you for the size and to find this entry in row 1, column 2. So take a minute and do that on your paper. And then on the second problem, what did you get for the dimensions? 3 by 2. Do I need you to write the 3 first? Yes, absolutely, right? And then the entry is lowercase c, 1, 2. So here's row 1, column 2. What's the entry where they intersect? -7. Okay, who got all that right? Okay, I'm not overly concerned with if you used a lowercase letter or you put A instead. I'm mostly concerned about if you got the entry correct, all right, on that. So don't worry about the other notation too much. Just as long as you understand it, it's fine. Mm-hmm. Yes, sir. Yeah. Okay, yes. Thank you. Okay. All right, so here we're talking about something called the diagonal of a matrix. This screen seems a little bit arbitrary, but it will make sense more later in the unit. We're sort of just introducing it right now for the concept and the vocabulary. A square matrix has, guess what kind of rows and columns? The same, right? The same. So the definition for a square matrix is it has the same number of rows and columns. And the reason why this would be important to us is because when we're solving systems, and by the way, again, matrices exist to make solving systems quicker and easier. And when we are solving systems, do you remember from last unit I would say, If we need to solve for 2 variables, we would need how many equations? If I need to solve for 3 variables, I would need how many equations? And so forth and so on. So you can kind of see where this idea of a square matrix would be useful. If you have 3 variables, you need 3 equations, okay? You would have to have those things be the same number. Diagonal entries, we talk about a lot when we are doing something called triangularizing the matrix, which we're not going to talk about today. But do you see how in this example on the I will statement, we have this here, there's zeros all under here in this little corner? Okay, so from here to here is called the diagonal of a matrix. And so this is a really great form to solve, which I'll talk about more in a bit, but it's sort of leading us into why we care about what a diagonal is in the first place. Because if we have that vocabulary, then I can say things like, we want to get zeros under the diagonal. The problem is, how do you know which diagonal? Because on a square, you can take a diagonal this way, you can take a diagonal this way. And then, furthermore, if I was asking you to list the entries on the diagonal, how would you know whether to go this way or this way? This way or this way. So in order to avoid confusion, it's been defined a certain way so that everyone's always on the same page when they're asking what the diagonals are. And so this definition right here, diagonal entries are the values on the diagonal from the upper left, I can't read, corner to the bottom right. Are there more than one of those ways to do a diagonal? Absolutely. But so that everyone's talking about the same thing, we're just going to use this convention. And it says only on a square matrix. Okay. So I won't be asking you for diagonals of something that's not square. I actually like that this is here. This is math notation. What do you think this is saying? All A sub ij where I equals to j. What do you think is going on? What is this notation trying to tell me? Then that's exactly right. Where the rows equal the columns, so it's a square. All right, so here we go. Is this a square matrix? Yeah. Okay. The rows and columns are the same. Identify the diagonal entries of the square matrix below. So we're going from which way to which way? Upper left to bottom right. And that starting here, ending there. And so all these problems are asking you to do is to just list them separated by a comma. 2, 4, -2. This is not a solution. It looks kind of like an ordered triple, right? But it's just we're only identifying the entries on the diagonal. By the way, real quickly, do you remember what all of these represent? X, that's right. So what are these? And what are these? The z's, right? We're going to talk in a second about, notice there's no straight bar with the constants on the right. So this is just a coefficient matrix, which we're going to talk about here in just a second. But one more time on here, when you're identifying the diagonals, entries, it's upper left to bottom right. And you're just listing it, 2, 4, -2. All right, right here. Right, lots of letters here. On this side, we have a linear system, like what we talked about last unit. Okay. No, there's no numbers, though. All the A, B, C represents coefficients, numbers that could possibly be there. On the right-hand side, I have 2 matrices. They're not connected. This one is called the coefficient matrix because what are all these? Coefficients. Coefficients come from the numbers in front of each of the variables. If you look here, ADG, ADG, this is all of your X coefficients, all of your Y coefficients, and all of your Z's. So really the variables and the pluses and stuff, they've just gone away. The only time you would see a sign here is if it was a negative number. And then this is the constant matrix, JKL, right? Those are the numbers without the variables that are on the right side of the equation. Right now in this form, they're separate from each other. Which one of these is squared, the coefficient or the constant matrix? The coefficient, right? Because you need 3 equations and 3 variables. And so the coefficient matrix, when we're solving, will always be squared. When we put these two things together into one huge matrix, hold on, I'll get right back to that. We call it an augmented matrix. Miss F talks, take 2. Okay, no, I can't. Okay, try it again. An augmented matrix is where the coefficient matrix here and the constant matrix are connected. We said earlier the straight line is like the equal sign, right, for a system of equations. And then don't forget about your brackets. Okay. It says dotted here, but we're going to do straight because it's faster to write straight than dotted when you're writing your matrices. But real quickly, so we're going to practice here in just a minute writing an augmented matrix from an actual system of equations. But this slide that I skipped a second ago, let's just fill that in real fast. If any of your linear equations do not include all 3 variables, okay, you have a z missing, an x or a y or something like that, you fill in a guess what in the matrix? A 0. Very good. Okay. You want to just leave it blank. You need numbers there for math. Okay, so you'd put a 0. The coefficients are always in the order x, y, and then z. Just quick side note, just to be sure you thought about those situations. Bless you. So, going to these 2 examples. Example top says, form the augmented matrix for the system and name the diagonal entries of the coefficient matrix. Okay, so I want you to take a minute and try that. You're going to write the augmented matrix of this system. And then over here, you're going to identify the diagonal entries on the coefficient matrix. I feel sad for the people watching the video. All right. What do you think this next example is asking? Write the corresponding system of equations for the matrix. What is that? What does that mean? Write the system by doing what? Putting the variables back in, putting the equal sign back in. So for example, this first, is this a row or a column right here? Row, right? For this first row, when I'm putting the variables back in, it would look like this. 1x plus 5y plus 1/2 z equals -24. No, you don't. I was just sort of driving home the point. That was a one. So you take a minute, write the other 2 equations, adding your variables back in. The cool thing about this particular matrix form is it's been triangularized, which means there's this triangle of zeros beneath the diagonal. And our matrices won't always be set up like that, but here's why it's great to get a matrix in this form if you can. Because what do you notice about that bottom equation? It's already solved for z. Okay, it's already solved. So we can just immediately begin back substituting to get our other variables. If z is 8, what's the next easiest variable to find? Y, because I would just do this and plug it into that one and simplify. So you do your math, I'll do my math, and we'll solve this system. And if you're multiplying fractions, you can do that a few ways. One is multiplying across the top and the bottom. So this would give me 24 over 4, which is 6. Another way is you have 3/4. 1/4 of 8 is 2, and you have 3, so that makes 6. Another way is you could simplify the 8 and the 4 and make that 2. All kinds of different ways to do fractions. So once I know that z is 8 and y is -8, then what? Plug them both into the first equation. So x plus 5y, which is now -8, plus 1/2 z, which was 8, is -24. We got 12. 12? And so we'll dive more into matrices tomorrow. Today was really just an introduction, vocabulary, concepts, basic rewriting. Okay, and we're not going to do the rest of the notes.